Welcome back, folks, to Chapter 9. We're talking about electricity and electric circuits. I have a little circuit analogy that I'd like to start with today. This document is sitting in the All Resources folder. So what I've got here is just a simple circuit with a battery, an ammeter, a resistor, and a voltmeter. And I want to show you again, nice little review, what are all these things actually doing? So remember, the job of a battery is to give charges, to give these coulombs, these big bundles of big bundles of electrons. Their job is to give them energy. So voltage is actually giving joules to every coulomb. And for example, a 9-volt battery is giving 9 joules to every big bundle of electrons, which we call a coulomb. So we've got these coulombs, which are moving through the circuit, and they've got this energy that they've been provided by or given by the battery. So they're moving along. There are ammeters in a circuit, which measure how many coulombs pass per second. They're measuring the rate of charge movement, how quickly things are moving in a circuit. We've got a resistor here. I haven't mentioned it, but the resistors are sort of burning up some of that energy or spending some of the energy that the coulombs are carrying. The voltmeter is doing a little check-in before and after to see how much of the energy the coulombs have lost at the resistor. So it takes a little measurement here and says, how many joules does each coulomb have? And then it takes another measurement after the resistor and says, well, how much do you have now? Because they will have spent some at the resistor. And then back to the battery. So that was moving current. Remember, that's Benjamin Franklin's big mistake. So he talked about things moving from positive to negative. And I threw this in there just as a review. Hey, those darn electrons, they go from the negative terminal, the small bar of the battery. They move around the other way. It turns out we're going to get into these circuit puzzles over the next couple videos. It doesn't really matter whether you think about things moving from the positive to the negative in this direction, or whether you want things to go from the negative to the positive the other way. It's going to work out both ways. That's a little bit confusing to think about, so here's an analogy for you. Let's think about the battery as a bank. And what's the job of a bank? Well, it gives customers money, right? You go to the bank. This is a special bank where we just make withdrawals. It's like the bank of mom and dad, where you only take money out. You never put money back in. Borrow, and I'm saying that in air quotes, means just, can I have some money and never repay you? It's already happening with my kids. So the bank, we're going to think about, instead of giving voltage or giving energy to coulombs, we're going to think about giving away money. And we're going to think of coulombs, these big bundles of electrons, as customers. Because, hey, you and I are made out of lots and lots of electrons. We're kind of like coulombs. So the bank is going to give dollars to customers, and then customers are going to go racing around in this circuit. We've got this little turnstile here. The actual function of a turnstile is just to measure how many people go past. It's not a rate movement. But for this analogy, let's say it's counting how many customers per second. So it's just like an ammeter, right? How many people are racing by every second. What this customer is going to do is they're going to go to the store. That's like our resistor. And at the store, you spend money, just like coulombs would spend energy at a resistor. So this customer here is going to go and spend some money. Now the voltmeter, which is this fellow here, I don't know if this is a large tumor or a nose or a deformed ear, but we're not going to judge, right? Try not to stare at it. We've got this wallet inspector. That's like the voltmeter. And that wallet inspector is going to stop this person before they go into the store, and they're going to say, hey, how much money do you have? And maybe that customer says, well, I've got $10. You're not going to rob me, are you? And the wallet inspector goes, no. And he just writes that down on a piece of paper. The customer goes into the store, spends some money, comes out, and goes, oh, shoot, there's that guy with the big tumor again. I got to not stare at it. And the wallet inspector says, excuse me, sir, how much money do you have now? And the guy goes, hey, leave me alone, man. I don't want any trouble. I spent all my money. I'm flat broke. The wallet inspector goes, no, that's okay. No trouble. And he writes that down in his little notepad. The job of a voltmeter is to check how much money do you have before a store versus how much money do you have after a store, right? How much money did you spend? Now it says here stores slow people down because you can't really run through a store. And what's weird about these stores is you have to spend money to get through them. You can't get through a store for free. There's no window shopping allowed in a circuit. There is another interesting thing here. Let's go back and say that this was a 9-volt battery. That would be like giving $9 to each customer. So you give $9 per customer. So every person who comes into the bank is going to withdraw $9 at a time, and they go racing off this way. In an electric circuit, by the time you get back to the bank, you are always flat broke. That's just how circuits work. You always have no money. You've spent it all. So there is $0 per customer by the time they get back to the bank. In a circuit, customers never make deposits. They only ever make withdrawals. So that means if you only hit one store along the way, how much money did you spend at that one store? Well, you had to spend $9. That's how this sort of spending works of energy. We're going to talk about it as spending of money because the analogy works nicely. So that means you would spend $9 at that store every time because you have to come back with $0. Now, some of you might be sitting there and saying, well, Mr. Heinrich, what happens if there's 2 stores? And the answer is, if those 2 stores are exactly the same, then you would spend $4.50 at one store, and you would spend $4.50 at the other store. Okay, fine. What if they're different stores? So what if it's like, I don't know, let's go with this analogy. What if there's the Golden Arches? So what if there is, let's think about these stores as restaurants. What if one of them is McDonald's, everybody's favorite? But what if the other one is like Earl's? We can agree that one of those stores is sort of a cheaper, less expensive store than the other. So that means your spending habits, you have to spend $9 in total, but it's not going to be 50-50 anymore. If you hit 2 different resistors, 2 different stores, then maybe we spend it, I don't know, maybe it's like $3 at McDonald's and $6 at Earl's or something like that. So you will have different spending habits if the stores are different. If there was a 3rd store there, then you'd have to spend your money 3 ways. Now keep in mind, you can't do this. You have to spend money to get through a store. So you are not allowed to do this. You are not allowed to spend all $9 at McDonald's and then just walk past Earl's or walk through it. It doesn't work that way. You always have to spend money in a store. It's weird, but that's just what circuits do. Sometimes students also ask, well, Mr. Heinrich, how does the current know that there's 2 stores? Well, the current doesn't know anything. That's like personification, right? It's just electrons moving. So they don't know how to spend. They don't know how many stores are there, but they follow the rules every time. I don't know how it works. It's just the way our universe is organized. It's very, very strange. But I'm going to use this analogy as we go through the notes today, and we'll keep that in mind that when we get back to a store, we have to have $0. Okay, moving on to Kirchoffs laws, the meat and potatoes of today's lesson. This is available. This is usually a handout I would give you. This is available in that All Resources folder. If you've got a printer at home, you might want to print it out, save you some drawing. If not, you can sketch these circuits. It's not a huge deal. There are a couple of tools. We're going to get into some circuit puzzles here. And I like to talk about developing this like circuit toolbox. We are going to put 3 tools in the toolbox. That's it. And that'll help us solve every puzzle. The first tool was Ohm's law. I equals V divided by R. Easy. Here are the next 2 tools, these things called Kirchoffs laws. So we've got a kind of crazy circuit going on here. You can go ahead and add those currents in. And I want you to take a look at those currents and see if you can figure out what's going on. The little black arrows show you which way the current is going. And this is current, not electrons, right? Because we're showing it going off the positive terminal, although it doesn't really matter. If you look at what's happening with the numbers, we have IT, which is the total current. We have 2 amps coming out of this battery. The 2 amps of current goes up the wire turns the corner, and then it hits this split right here, which we call a junction. And that current is going to divide up, kind of like how a river would divide up to go around a little island. And if you look at the values for the split, it doesn't split 50-50, but we have 1.5 amps going down through this left-hand branch, and then we have only 0.5 amps going on the right-hand side. Now, if you look at those resistor values, maybe that makes sense. 8 ohms of resistance is less than 24 ohms. So that means you're going to have more current flowing where it's easier, and less current flowing through where there's a bigger, harder resistor. So that current splits, not 50-50, because the resistors are different. And then what's really cool is we get to another junction. So that current comes into a junction again, and it actually combines back together. And when it combines back to the full 2 amps, back to the original current. So I want you to keep in mind that in a circuit, current will split, but it always comes back together. You don't actually lose current anywhere in a circuit. Whatever the current was leaving the battery, that same current's going to come back to the battery. So here we're back to a full 2 amps. It rolls through resistor 3, and then bang, it runs into another junction. And it splits again. Some of it goes left, some of it goes right. And you can see here the split's different. 0.8 amps going left, 1.2 amps going to the right. Don't worry about where those numbers came from. The important part is we haven't lost any current, and eventually that current is going to come back into this junction, and it's actually going to combine back to the full 2.0 amps. So in this circuit, we have taken our total current, which was 2 amps, and it's divided itself up in a couple of places, but it always combines back together, and then it's split again, and then it combines back together. You still are going to have 2 amps of current arriving back to your battery. So the first of Kirchoffs' laws, which I guess is the second tool in the toolbox, we call current law. I like to just call it junctions. And that says at any junction, and a junction is just where wires either split, like right there where I put that first black dot, or right here where wires actually combine back together. At any junction, the current that comes into it is equal to the current that goes out. So if you know like 2 out of the 3 pathways, you can always solve for the third. And we'll see what that looks like in practice in a few minutes. The second of Kirchoffs' laws is called the voltage law, or loops. So you can go ahead and add these green voltages in. And what I want you to do is I want you to think about, we're going to go back to that analogy, I want you to think about a shopping trip. So we leave the bank with 40 bucks in our pocket, 40 volts. And we know that we have to get back to the battery with $0, because that's what current does in a circuit. It is always, it spends all of its money, spends all of its voltage. We never lose current, but we always lose all of our voltage. We spend all of our money. We're terrible at saving. So a loop says, I want you to trace a possible path you could take if you go on a shopping trip. So maybe we go up here, we turn the corner, we turn the other corner, and let's go left. So we go this way. We spend $12. Then we're going to go this way. You can't backtrack in a circuit. You can't just sort of sit here and go around in circles. You have to honor the arrows. It's all one-way streets. So we hit store number 1, and then we're going to travel this way. We're going to hit, maybe I'll put some arrows so we can see which way we're going. You don't have to draw this in either, by the way. We hit store number 3. We spend $4. That's $16 in total. And then let's go left again. We like to go left. We hit store number 4. We spend $24. And if you run those numbers, that takes us all the way back to the battery. 12 plus 4 plus 24, you spent your 40 bucks. It's perfect. You have to spend all your money. So voltage law, which I like to call loops, says that if you trace a loop for current, the charge in a circuit, and again, that was only one option, right? You could have gone left and then down and then right. but you can't backtrack, so we can't hit 5 and 4 in the same trip, right? But you could have spent, in that fashion, 12 plus 4 plus 24, you still spend your 40 bucks. So loops says this. It says around any loop, and you want to physically like trace it out with your finger or your pen just like I did. Around any loop, the total voltage that you gained, which is whatever you left the battery with, you have to spend at all the stores. That's what a loop says. Around any loop, you got to spend all your cash. It's kind of fun, right? It's like unlimited spending all the time. So that's the second of Kirchoffs' laws. That's the third tool in the toolbox. That's going to help us solve all kinds of cool circuit puzzles. Before we jump into the puzzles, though, I want to review quickly. You may have seen this in junior science. What are the differences and similarities between series and parallel circuits? So in a series circuit, that means you have resistors. Could be 2, could be 3, could be 17. You've got resistors in a line. When I say resistors in a line, they cannot have junctions in between them. So that means if you go through resistor 1, you have to go to resistor 2. And if you're at resistor 2, you have to go to resistor 3. If you have a split, a junction in between those resistors, then they're not in series anymore. So they're resistors in a line with no junctions in between them. Because there are no junctions, that means all the currents are going to be the same. So the other thing I should mention about current is if we have 2 amps of current, go back to the same value we had in the first example there. If we have 2 amps of current leaving the battery, that 2 amps of current doesn't come racing off of the battery and then hit resistor 1 and slow down. And then hit resistor 2 and slow down even more. And then hit resistor 3 and slow down even further. It's the same as when I go for a run. I don't leave the school. If I'm going to go run 10 kilometers, I don't leave the school at a sprint and then progressively slow down because I'm tiring out and end up just like crawling back to the school. I pace myself. I try to go like the same pace generally the whole time. And it turns out current does exactly the same thing. So if you have 2 amps of current, it is going to pace itself. You will have 2 amps of current no matter where you choose to measure it in this circuit. So it doesn't slow down when it hits a resistor. It paces itself. There will be 2 amps no matter where you put your ammeter. So keep that in mind about current. It paces itself. And the only time we change current, remember we don't spend it. We spend voltage, but we don't spend current in a circuit. We don't lose any, right? And that's what I mean by spending it. So if you have 2 amps of current leaving the battery, you have to have 2 amps of current coming back to the battery. So we don't spend it anywhere, we don't lose it. And in this case, there was no opportunity for it to split up like it did in that Kirchoffs law picture that we just looked at. So it's the same, no matter where you choose to measure. One crappy thing about series circuits, pardon my language, I should have said maybe one bad thing, is if one resistor fails. So if resistor 1 breaks and doesn't work, then that means current can't get past it and the whole circuit stops. Old strands of Christmas lights were like that. One bulb would burn out and the whole strand would go out, and then you'd have to figure out which individual bulb was the faulty bulb. It was pretty crummy. The voltage drops, though, how much money you spend at the resistors is usually different because the resistors are usually different. So if we are left with 9 volts off of this battery, the only way that we could spend it as 3 volts and 3 volts and 3 volts is if the resistors were all identical. But if those are 3 different stores, like McDonald's and Earl's and what would a really expensive one be? I don't know. Pick a really expensive restaurant. I don't go to them, so I don't know what they are. The now closed Burger 55. Then maybe the spending would be like $1 and $3 and $5. I think that adds up, $5. So if the resistors are different, you're going to spend that money differently. Now, the last thing I need to show you with series circuits is how do you figure out the total resistance? So if you have those 3 resistors sitting there in series, here's what you need to do. It's actually really easy. To find the total resistance for resistors in series, you simply add up the resistors. How many ohms each of them are, oops, it would look like that. R1 plus R2 plus R3. So for example, if we had 10 ohms and 20 ohms and 30 ohms, then our total resistance would simply be 10 plus 20 plus 30. That is equal to 60 ohms of resistance. And that's in effect what the battery feels. That's how the battery paces itself with the current, is it feels what the total resistance is. I know I'm personifying the battery again. The battery doesn't feel anything, but that's just an analogy that works. So the total resistance there is 60 ohms. Let's look at a parallel circuit. So we'll skip that. Here you go, parallel circuits. That means resistors side by side, like it shows in this picture. And what you have to have with parallel resistors is only wire connecting their tops and bottoms. So if you look at resistors 1 and 2, there's only wire connecting their tops and only wire connecting their bottoms, parallel. What if we look at resistors 2 and 3? There's only wires connecting their tops, only wires connecting their bottoms, parallel. But if I were to go and do this, if I added a resistor 4, you could look at 1 and 2 and say, okay, wire connecting their tops, wire connecting their bottoms, yes indeed they're parallel. But if you now look at 2 and 3, you've got wire connecting their bottoms, but you've got a resistor connecting their tops. So you actually would not be able to say that resistors 2 and 3 are in parallel. There actually is no relationship between 2 and 3. And I might as well point it out because I bet some of you are seeing it. There is a relationship, though, between 3 and 4. If you look at 3 and 4, there is 2 resistors in a line with no junctions in between them, right? If I go through resistor 4, I have nowhere to go but resistor 3. So now we could say, well, 1 and 2 are in parallel, but 4 and 3, or 3 and 4, whichever order you want, they're in series. So don't be phased with series. I maybe should have mentioned it in the previous page, that you can bend the wire. That's totally fine, and still have resistors in series. I'm going to take that out of there. Some more information about parallel resistors or parallel circuits. There you go, connected with wires before and after. All the voltage drops are the same. Check this out. This is really cool. This is Kirchoffs' laws. What if we have a 9-volt battery? Remember voltage? That was loops. And we said around any loop you have to spend all your money. So you say, okay, let's go on a shopping trip. Here's the easiest one. That's a shopping trip we could go on. We left with $9 in our pocket. We only hit one store. So how much money did we spend? Well, you had to spend $9. Okay, let's go on another shopping trip. Maybe we decide to walk a little bit further. We go on this shopping trip. You left with $9 in your pocket. You only hit one store, which means you had to spend $9. Hey, equal voltage drops. And here's the last one. There are 3 possibilities for shopping trips. There are 3 loops you can take. And you left with $9 in your pocket. You only hit one store. You had to spend $9. So it's kind of cool, right? Loops shows you that for resistors in parallel, you got to spend the same at all of them. The voltage drops or your spending habits are identical. So that's proof with loops, or proved by loops. One cool thing about parallel circuits, this is how almost all of your house is wired up, is if one of them stops functioning, like if R1 goes out, then current will stop going down through resistor 1. So current says, no, I'm not going there, but current can quite happily keep going through resistors 2 and it can quite happily keep going through resistor 3. So the other two can continue. Let me show you, last thing on this page, how do you find total resistance? This is a little bit more work, and I want you to humor me and get your calculator out for this one. To find total resistance, it looks a lot like we did with our series resistors, R1 plus R2 plus R3. But there's a difference. The difference is we inverse all of them. We reciprocal every one of those resistors. So let's try this out. I want to show you what this looks like, and it'll make more sense if you've got your calculator. Let's go with the same values, 10 ohms, 20 ohms, 30 ohms. Here's how we would find the total resistance. We'd say 1 over RT is equal to 1 over 10 plus 1 over 20 plus 1 over 30. So on your calculator, here's what you can do if you want. You can actually type it in as 1 over 10 plus 1 over 20 plus 1 over 30, and you get that decimal. That's actually not the total resistance. Maybe let me just show you what that is. The 0.1833, that's still 1 over RT. And in order to get the total resistance, we now have to take 1 over that answer. So you add the reciprocals, and then you take the reciprocal. It's a bit time consuming, but you'll have it down in no time. There's the total resistance we're after. The total resistance in this circuit would be 5.45 amps. That's what the battery in effect feels like it's pushing against. Has no idea that there's 3 resistors in parallel. It just feels 5.45 amps, and then it sends out an appropriate amount of current based on that resistance. On your calculator, for sure on a graphing calculator, you've actually got a reciprocal button, which is kind of slick. So another way to just type this in your calculator would be to say, hey, take the inverse of 10 and the inverse of 20 and the inverse of 30. There's my 0.1833. And then please just take the inverse of that answer. There's your 5.45. So that's just a quicker way of sort of calculating your total resistance with parallel resistors. Now, I don't know how long I can record video for, so that's actually part of the first lesson. I am going to stop right here, upload this video, and then we will continue with some circuit puzzles because we're ready to go, and I'm actually pretty darn excited about it. Hopefully you guys are going to be too. I'm actually jazzed. I'm not just saying that. You think I'm a dork. I'm totally okay with that. Check out the next video to learn how the puzzles work.